Welcome to the first video of the course. I encourage you to get out a piece of paper to be able to take notes. While you're taking notes, be sure to jot down questions. We have a discussion forum on D2L to be able to discuss questions that you might have. Another thing that I encourage you to do is to pause the video frequently. There will be times when I move faster than what you're able to process or write, and that's why this video is taking place virtually. You have independence to be able to do what you want to do when viewing the video. I also encourage you to pay close attention to the video. It's easy to be distracted and to try to multitask while watching math. And because you're going to be held accountable not only for watching the video, but for learning the material in the video, I highly recommend that you set other distractions aside and just focus on learning math when it's time to learn math. So, let's go ahead and start. Today, we're going to be talking about dot products and cross products. These are topics from 12.3 and 12.4 in your textbooks. I encourage you to look through the text as well if you have further questions that aren't answered in the video. Our learning goals for today are to compute the dot product, to understand the geometry of the dot product. We're going to talk about an application of dot products, which is projections. We're going to talk about both the algebraic and the geometric construction of projections. Next, we're going to talk about cross products. I want you to be able to compute them, as well as the geometric interpretation of cross products. And there are a couple of neat applications of cross products. We'll see more of them later on in the term as well. But today we're going to talk about the area of a parallelogram in depth, and we're also going to touch on how to compute the volume of a parallelepiped. And that's something that you'll explore a little more in your homework as well. Our first topic is dot product. The dot product is an operation that you can do on two vectors. So let's say that I have a vector v, and I'm going to represent my vector v as having a first component v1, a second component v2, and a third component v3. And let's say that I have some other vector, vector w, and my vector w has components w1, w2, and w3. What does my dot product operation look like? It's written v dotted with w, as you might be able to guess, and it's computed by taking the first two components and multiplying them together, v1 times w1, and then adding the product of the next two components, v2 times w2, and then adding the third components, which is v3 times w3. Simple enough. Let's see an example. Let's say that my v component, here's my example. My v vector is given by the vector 3, -1, 4, and my w vector is given by -2, -1, 5. Then when I take the dot product, v dotted with w, I can rewrite that as 3, -1, 4, dotted with -2, -1, 5, and I'm going to take the dot product, just as described above, by multiplying the first components together. 3 times -2 gives me -6. Adding the second components multiplied together, -1 times -1 is +1, and then the third components multiplied together. 4 times 5 is 20. And when I add these three things together, I get -6 plus 1 is -5, plus 20 is 15. Note, I started with vectors, but what I got out was just a number, that the output of the dot product is always just a real number. The output of the dot product is a real number. And the input is always vectors. We're talking about vector operations. Let's see another interesting application. Suppose that I have a vector v and a vector w that are parallel to one another. I wonder what the dot product looks like in that case. So let's suppose v and w are parallel. I want to do this in generic land. So what does it mean for a vector v and a vector w to be parallel to one another? We talked about that last time. It means that I can take v and multiply it by some scalar. Let's say I multiply it by v multiplied by some number t is going to be equal to w, meaning that I'm not changing the components, I'm just shrinking or growing v until it gets to be exactly w's length. And that's what it means to be parallel. So when I take the dot product here, instead of dotting v dotting with w, I'm going to dot v with v times t. And if I write this out in the same notation that I was using previously, in this case it means that it's going to be v1, v2, v3 dotted with, what is t times v? It's going to be t times v1, t times v2, t times v3. Which in this case is going to be equal to, it's v1 times t times v1, which is tv1 squared plus tv2 squared plus tv3 squared. I can factor out the t, and I get t times v1 squared plus v2 squared plus v3 squared. Maybe this isn't that interesting the way that it's written, but there's sort of a cool connection here. Notice, maybe you don't notice, I could rewrite this in a crazy clever way. This is the square root of this squared, meaning I'm just going to take the square root of this big chunk and multiply it by itself, because I can square root something and square it. v1 plus v2 plus v3, and v1 plus v2 plus v3, all of the terms squared. Why did I do this? Notice that the square root of v1 plus v2 plus v3 squared, when each of these are squared, this is something that we've seen before. This is actually the magnitude of v1. And this is the magnitude of v1 a second time. And when I look at t times the magnitude of v1, well, that's just the magnitude of w. So notice that there's a geometric implication here. By writing it this way, we see that this term is actually the magnitude of w, and that this is the magnitude of v. So we just found out that if v and w are parallel, then the dot product is actually just the magnitude of w times the magnitude of v. Notice that this is a special case where these two are parallel. What is the geometry in general? This gets to our next theorem. Theorem that when the dot product, a vector v dotted with a vector w, is going to be exactly equal to the magnitude of the vector v times the magnitude of the vector w times the cosine of the angle between them. We just saw an example where the vectors were parallel to one another. When they're parallel to one another, the angle between them is actually 0. And what's the cosine of 0? The cosine of 0 is 1. So we just saw a special case in which when v and w, maybe I should say when v and w are parallel, then the angle between them is 0. So the cosine of theta is the cosine of 0, which is 1. And we find that v dotted with w is actually just the magnitude of v times the magnitude of w times 1. Let's go ahead, instead of deriving this as a theorem, we're instead going to see an application of it. So let's start with an example. Let's say that I have my vector v is the vector, I actually wrote out this example maybe. 1, 0, 5. Whoops. And my vector w is going to be given by the vector -3, 2, 4. Let's find the angle between these two vectors. So we know that in order to find the angle, I'm thinking of both of these vectors as having the same point of origin, and they're pointing out, this one's pointing out 1, 0, 5, and this one's pointing out -3, 2, 4. It's not helpful for me to actually draw them because I find that drawing three-dimensional vectors on two-dimensional space, it doesn't actually give me that much insight into which direction they're pointing. So in order to find the angle between these vectors, I'm going to use the dot product. So we know that the dot product is going to be equal to the magnitude of each of them times the cosine of theta. Let's do a little algebra before we get going to simplify what this looks like. This means that if I divide both sides by these magnitudes, I see that the cosine of the angle between them, the cosine of theta, is going to be equal to v dotted with w, all divided by the magnitude of v times the magnitude of w. So if I want to solve to find out what this angle theta is going to be, in general, theta is always going to be equal to the inverse cosine of v dotted with w divided by the magnitude of each of these vectors. I have to be a little cautious. Whenever I'm taking an inverse cosine, it's always going to give you outputs that are in those initial angles. And so you do have to look at the geometry. Careful when taking inverse trig functions. That it'll only give you the angle that goes from -pi to pi, and it might be that you want an angle that's bigger than that. Let's use this information to actually compute the angle. So, continuing this example, I'm going to look at the dot product, v dotted with w, which in this case is 1, 0, 5, dotted with -3, 2, 4. When I take this dot product, the first term multiplied together is -3, the second terms multiplied together gives me 0, and the last components multiplied together gives me 20. So this gives me positive 17. That's one piece. That's this dot product piece. We also need to know what's the magnitude of v. That's the length of v. And we're going to use our three-dimensional Pythagorean theorem to find out that it's going to be 1 squared plus 0 squared plus 5 squared, which is the square root of 26. The magnitude of w is going to be the square root of -3 squared plus 2 squared plus 4 squared, which is the square root of 9 plus 4 plus 16, which is the square root of 29. So that means that our angle in this case, theta, is just going to be the inverse cosine of our dot product, which in this case was 17, divided by each of these magnitudes multiplied by one another, which I'm not going to multiply. If you have a calculator, you can multiply this out. If you had a calculator, you could also simplify it. In general, maybe I'll pause. I'm going to pause. Now, you get to learn something about my teaching. This, to me, is a much better solution than some crazy decimal approximation that you got out of your calculator. This lets me know that you have gone through the steps and you understand what each of these pieces are. When you do a decimal approximation on your calculator, sometimes that's helpful and sometimes it's less helpful. So I will always accept full credit when you leave answers written as exact answers rather than decimal approximations that you plugged in your calculator. That's the end of my rant.